High above the planet, encircling the Arctic like an invisible fortress, there exists a vast river of air. Most of the time, it spins quietly, holding the cold of the far north in place. But when that system falters, when its balance is disturbed, the effects are felt across continents. Snow drifts into regions unaccustomed to it. Ice coats landscapes that rarely freeze. Winds carry Arctic air far beyond its usual boundaries. This is the story of a disrupted polar vortex and of forces that originate far beyond Earth itself. To understand what unfolds on the ground, we must first step upward into the layered structure of the atmosphere. Closest to the surface lies the troposphere, the dense region where weather forms and where life unfolds. Above it sits the stratosphere, thinner, colder, and usually more stable. The polar vortex spans both of these layers. It is not a single storm, but a circulation, an organized spinning reservoir of cold air centered near the pole. When stable, it acts like a lid, containing the cold and guiding the jet stream along a relatively smooth path. But stability is not guaranteed. When the polar vortex weakens or splits, the jet stream begins to meander like a slow, looping river. Cold air spills southward in long arcs, while warmer air surges north into regions that are usually locked in ice. This exchange reshapes weather patterns across the entire northern hemisphere. In this episode of Disruption, the signatures are unmistakable. Snow blankets high latitudes as expected, but it also extends far beyond them. Eurasia plunges into deep cold. North America sees frigid air reaching well into southern regions. Across northern Europe, temperatures drop sharply, while areas that are normally colder experience anomalous warmth. These contrasts are not random. They are the fingerprints of a polar vortex that has lost its symmetry. Russia's far eastern regions face snowfall unseen in decades. Japan experiences relentless winter conditions, with heavy accumulation across wide areas. The United Kingdom braces for widespread snow, with ice and freezing winds sweeping across nearly the entire country. In the United States, millions contend with power outages, hazardous roads, and ice storms in regions ill-equipped for such extremes. At first glance, this appears to be an atmospheric story alone. But the roots of this disruption reach much farther, outward, into near-Earth space. Earth is not isolated. It is immersed in a constant flow of particles streaming from the sun, known as the solar wind. Most of the time, this wind is relatively gentle, deflected by Earth's magnetic field and guided harmlessly around the planet. But when the sun releases a powerful burst of energy, a solar storm, that interaction changes dramatically. During an exceptionally intense solar event, torrents of high-energy particles surge toward Earth. These particles are electrically charged, and because of that charge, they are steered not by gravity but by magnetism. Earth's magnetic field funnels them toward two regions near the poles, known as magnetic cusps. In the northern hemisphere, this cusp lies strikingly close to where the polar vortex is anchored. The overlap is not coincidental. When a severe radiation storm arrives, energetic protons and ions penetrate deep into the upper atmosphere. Under extreme conditions, they reach down into the stratosphere, the very layer that forms the upper boundary of the polar vortex. This is where space weather and terrestrial weather intersect. The storm in question ranks among the most powerful radiation events ever recorded. Proton flux increases by orders of magnitude, meaning the atmosphere is suddenly bombarded by vastly more energetic particles than normal. The interplanetary magnetic field surges to extraordinary strength, compressing Earth's magnetosphere and injecting immense energy into near-Earth space. Although the storm's magnetic orientation limits the worst technological impacts, its energetic input is undeniable. The magnetosphere absorbs this energy, stores it, and then releases it gradually over time. The result is not a brief flash, but a lingering transformation of Earth's radiation environment. As these particles cascade into the atmosphere, they collide with molecules, triggering chains of ionization. One energetic particle can set off thousands of secondary interactions. Electron densities shift. Atmospheric conductivity changes. Electrical currents between the ground and the ionosphere intensify. These electrical processes matter more than they might seem. Ice particles within clouds naturally accumulate charge as they collide and rub against one another. When the surrounding atmosphere is already electrically energized, this charging accelerates. Storm systems become more volatile. Snowfall intensifies. Ice formation becomes more efficient. The atmosphere, in effect, becomes primed for extremes. This helps explain an otherwise rare phenomenon: lightning during a snowstorm. In southern regions unaccustomed to frozen precipitation, flashes of lightning illuminate icy skies accompanied by thunder. Such events require significant electrical energy that is not typically present in winter systems. Their appearance serves as a visible clue that the atmosphere is operating in an unusually energized state. Meanwhile, above the planet, the consequences of the solar storm continue to unfold. Earth's radiation belts, vast zones of trapped energetic particles, are reshaped. Particles penetrate regions they normally cannot reach. Some become trapped for months or even years, slowly altering the background radiation environment. These are not fleeting changes. Research shows that after storms of this magnitude, elevated particle fluxes can persist long after the initial impact fades. The magnetosphere does not simply reset. It relaxes gradually over extended periods. This long recovery matters for the polar vortex. The vortex depends on a delicate balance between temperature, pressure, and atmospheric circulation across multiple layers. When the stratosphere becomes more energetically disturbed, that balance is harder to maintain. The vortex becomes more prone to splitting, wobbling, and weakening. Each disruption increases the likelihood of further instability. Visualizations of the atmosphere reveal this clearly. At the highest stratospheric levels, the vortex plunges southward in deep troughs. At lower levels, closer to where weather forms, the disruptions grow more pronounced. The circulation bifurcates, splitting into separate lobes, allowing cold air to spill outward while warm air intrudes poleward. And directly above this fractured system lies the magnetic cusp, channeling energy from space into the very region where the vortex is unraveling. This does not mean that space weather creates snowstorms from nothing. Atmospheric patterns must already be in place, but intense solar activity can amplify what exists, adding energy, increasing volatility, and prolonging disruption. It acts as a catalyst, not a scriptwriter. The broader implication is subtle but profound. Weather forecasting often looks days ahead, sometimes a week, but the processes set in motion here operate on much longer timescales. Weeks turn into months. Seasonal patterns shift. The atmosphere remembers. As winter progresses and transitions toward spring, the northern hemisphere remains vulnerable to further volatility. Each additional disturbance compounds the instability already present. Snowstorms grow heavier. Cold snaps reach farther south. Contrasts sharpen between regions locked in deep freeze and those experiencing unusual warmth. Above it all, faint glows linger in the night sky, soft greens and reds visible long after auroras fade. This afterglow is not merely beautiful, it is evidence of energy still being released from Earth's magnetic cocoon, a reminder that the planet is still adjusting. The polar vortex, once a quiet guardian of Arctic cold, becomes a dynamic participant in a much larger system, one that connects the surface of the sun to the weather outside our doors. And as this story continues to unfold, it offers a powerful lesson. Earth's atmosphere does not operate in isolation. It is part of a vast, interconnected environment where space and weather are inseparable threads in the same tapestry. Understanding that connection does not just explain the storms of one season, it reshapes how we view the planet itself, suspended within a living, energetic cosmos.